So today we want to talk about the speed of sound waves. Last time we talked about waves on a string and we saw tension was one factor that affected how quick they traveled. The other factor was the linear density. The more dense the string was, the slower the wave traveled. We had a formula, tension in newtons divided by linear density in kilograms per meter. This would then tell us how quickly the wave propagated down the string. Sound waves are going to be traveling at different speeds depending on the material that they're traveling through. So they start with an oscillating source, like a speaker or a tuning fork. They then propagate outward through the material that is carrying the sound wave. So if we're talking about air, as the speaker moves forward and backwards, it compresses the air and then pulls back. Compresses the air and pulls back. These compressions then travel outward. Again, it's the energy pulse, not the actual particles, creating areas of high and low pressure. Okay, so this is what our sound wave looks like. We can animate this something like this. So as the sound wave is being produced, we get compressions that travel to the right, and then areas where the pressure is lower also traveling to the right. You'll notice that the particles themselves don't move. All that moves is the energy pulse as it compresses and spreads the particles apart. Okay, first thing to know about the speed of sound is that it's much slower than light. So even though sound travels nearly instantaneously, on a larger scale, we can see that it's actually kind of slow. So when we get a lightning strike, boom, even though everybody's going to see the lightning at almost the exact same time, the thunder is going to take quite a while to travel to different locations. Sound is slower than light. Sound travels different speeds through different materials. We mentioned that a moment ago. So sound travels faster through liquids than it does through air. Sound travels fastest in solids. So if we look at solids, the molecules are close together. At air, with liquids, they're farther apart. And with gases, they're really far apart. Think of it like dominoes. If the dominoes are close together, the energy pulse can travel quickly. And the farther apart the dominoes are, the slower the energy pulse is going to travel. So steel, it travels fast, and with air or any other gas, it's going to travel slower. It all has to do with how tightly packed the molecules are and the elasticity between the molecules. We have a chart on one of your reference sheets that shows the speed of sound through different materials. You'll notice gases are slow, solids are going to be fast, and liquids somewhere in between. The one we want to focus on is air, and with air, the speed changes with temperature. So depending on how hot it is outside is going to determine how quickly the sound travels. Okay, so as the temperature goes up, the speed of sound goes up by a little bit. Sound in space, you should realize, does not exist. Since there are no particles in the vacuum of space, the sound has nothing to carry it from place to place. Okay, I'd like you to try a few problems. So we have this video of an explosion where a demolition team is trying to get rid of an old water tower. It takes 1.75 seconds for the sound to reach us. And the temperature of the air is about 42 degrees Celsius. Okay, so if that video actually played properly, you would have seen the explosion first, and then later you would have heard the sound arrive. So figure out how far away we were from that explosion based on the time and temperature. Then I'd like you to try and find the speed of sound on Mars. So we're going to imagine a rover sending a signal back to a base station, and we're going to have the sound wave take a distance of 350 meters and a time of 1.4 seconds. Use this to figure out the speed of sound on Mars. It'll be different because of the different composition of the atmosphere and the different concentration of the particles in the atmosphere. So find the speed of sound on Mars. Finally, imagine you're out playing soccer. You see a lightning strike. You count between when you see the strike and when you hear the thunder. It's 6.4 seconds. The temperature is 32 degrees Celsius. Find out how far away that lightning strike actually was. So try these problems and see how you make out.